Hello. Today we will be discussing about the dual formulation of the SVM optimization problem. The aim has been for the SVM classifier to find the hyperplane with the maximum margin. Now, the objective function obtained was this: the minimum of half of the norm W squared, which we had seen in the last video, and the linear constraints are as stated. We had seen that the total distance between H0 and H1 and H2, that is the total margin represented here, is 2 by norm of W. And this is a constraint optimization problem with n linear constraints. Now we aim to obtain the dual formulation of the minimization problem using Lagrangian multipliers. This, as we have mentioned earlier, is to get a intuition about what is actually happening in this classification method. So these Lagrange multipliers alpha I, one each for the n constraints we take, such that the Karish-Cohn-Tucker conditions are satisfied at the optimal solution, which is these two conditions. Alpha I multiplied by the constraint equal to 0, and all the alpha i's are greater than equal to 0. Okay. So, I'm sorry, this should be Mushkun-Tucker. Conditions are satisfied at the optimum. Now, the new objective function incorporating all the constraints, we call it the Lagrangian, becomes minimize L equal to half the objective function which we had written squared of norm of W minus these set of constraints each multiplied by alpha I. And L should be minimized with respect to WB and maximized with respect to alpha I. Now, the dual Lagrangian objective function, which we obtain after we have done some manipulations, arithmetic manipulations on the previously written objective function, is as written here. We shall discuss some details in another video. But for now, we can just look at the dual objective function which we have obtained, and the linear constraints are alpha I greater than equal to 0, and this the product of alpha I by I summed over all the samples will be 0. Now, this L dual function which we have obtained, we can see that it is the summation over all the samples, double summation over all the samples of the pairs of samples rather. See, we are taking pairs of samples uh, indexed by I and j. So alpha I, alpha j, the two multipliers for the two samples, and the yi, yj, which are the labels, and the dot product of the xi and xj. So what this is the kind of intuition for which we ventured on for this discussion. Is the interesting part here is that we don't have any w's in our this formulation of the dual objective function, dual Lagrangian, and in fact the optimization depends on the dot products of pairs of samples. So this is a very simple outcome of the our discussions, that the dot product of pairs of samples plays an important role in the SVM classifier. Okay, so having obtained this dual function, now we can solve it for the alpha i's using the standard optimization techniques, and having obtained this alpha I, we shall be able to compute the W and B, as we shall see shortly in the next video, which will give us the hyperplane with the maximum margin. So, we have gone through the discussions of SVM of finding the optimization problem in terms of minimizing the norm of W squared under the linear constraints. And then we found the dual formulation in terms of the Lagrangian objective function. We use the Lagrange multipliers, and this brought us to the approach brought us to this formulation where we can see that the dot products of pairs of samples plays an important role. Okay, so we shall proceed in the next video for the next steps. Thank you. Thanks for watching.